Hello everyone, today I want to talk about some numerical studies on flow and heat transfers in membranes, helical-coil, and serpentine-tube heat exchangers. So we know that the membrane helical-coil heat exchangers is used for the waste heat recovery system due to its high overall heat transfer coefficient and compact configuration. So the previous researches show that the average heat transfer coefficient of the membrane helical-coil outer surface is higher than that of the membrane serpentine-tube. However, the heat transfer enhancement mechanism has not been totally understood. So I think that might be a good field to do some research. So the object is to numerically study the heat transfer and flows in the heat exchangers consisting of the membrane helical-coils and the membrane's serpentine tubes. So first let's see some description of heat exchangers. So the started exchangers consist of 3 membrane helical coils or membrane serpentine tubes. So this is the figure 1. So the figure 1 shows the geometrical configuration of the membrane's helical coil, and the geometry is consistent for membrane's helical coil heat exchangers. So it's shown in here. Okay, so this pictures illustrates that the investigated the membrane's serpentine tube heat exchangers. So all right. So next we see some kind of mathematical information. So in the present study, So in the present studies, the flow is considered to be steady. Okay. So and the pressure variations in heat exchangers are so small, and the Mach number of the C-gas is so low that the C-gas flows can be considered to be incompressible ideal gas. So at the inlet, the C-gas with temperatures T0 enters the heat exchanger at the velocity of the U0. So the flows is assumed to be steady. So the governing equations describing flows and heat transfers are the conservational equations for mass, momentum, and energy. So which are developed from the conservation laws of the physicals. So this here shows some equations, continuity, momentum, and energy equations. Okay, so we know that the key is the thermal conductivity, right, and the Planck number. Okay, this is the thermal conductivity, and this is the turbulent Planck number, so which is used as a constant in our simulation. Okay, so the uniform profiles at the inlet boundary condition and the diffusion flux at the outlet are shown here. So this is the boundary condition. Okay, so okay, next we see some numerical simulations. The 3-dimensional numerical simulations of the flows and heat transfers in heat exchangers were obtained using a commercial CFD package. Okay, so the cyclic algorithm was used to resolve the coupling between the velocity and pressure. So this shows us the local grid topologies on membranes helical-coil. So the grid independent test indicate that we already did independent test, grid independent test. I won't talk more in here. So at the inlet, the syngas with temperatures T0 enters into the heat exchangers. So it's about I think it's 873 kilograms. So the word temperature of the membrane coil and the tubes assumed to be uniform, so which equals to TW. Okay, so this figure 6, okay, is the surface heat transfer coefficient. So which was calculated from the inlet and outlet temperatures data and the flow rate. Okay, so when delta Tm is the logarithm and temperature differences, so the surface heat transfer rates were based on the outer surface area. So of the membrane's helical coil or membrane's serpentine-tube, so the delta Tm was calculated based on the same gas inlet temperatures, T0. So we calculated according to this. So the outlet of the temperatures T out and the wall temperature of the T wall. Okay. So next we see some result. Okay. Firstly, in order to verify the present numerical work, so the model validation is conducted first. So experiments have been carried out to study the heat transfer of the membrane's helical-coil heat exchangers. So the we can see that from this picture, okay. So the gas pressure varies from the 0.5 pascal to 3.0 pascal, and gas inlet velocity varies from the 1.5 to 3.0. So the uncertainties of average Nussels number and Reynolds numbers were less than 4.2% and 3.4% respectively. So, okay, so the heat transfer correlation of the membrane's helical-coil heat exchangers is obtained from this figure, okay? So, this figure shows the comparisons between the present numerical values and the predicted result by the experimental heat transfer correlation. So we can see that the maximal derivation between the simulated prediction and experimental correlation is less than 5%. Okay, so therefore, I think that the simulations have the good predictions of the experimental correlation. Okay, so next we're going to see heat transfer coefficient. Okay. Okay, so these figures show that the numerical obtained average heat transfer coefficient, HT. Okay, so this will be HT of the inner coil. So the intermediate coil and the outer coils and the heat exchangers. So from the figures, it can be observed that HT increased with the increase of the operation pressures under the semi-light single velocity. So it demonstrated that the higher operation pressure can improve the heat transfer, which is attributed to the differences in the syngas mass flow rate. Okay, so finally, we see some tangential velocity distribution. This is the tangential velocity distributions with different pressure. So for the figures, it can be observed that the UT, the velocities in the annulus channel, is independent of the increase of the operation pressure, which demonstrated that higher operation pressures cannot change the velocity fields in heat exchanger, but can improve the heat transfer due to the increase of the sinus mass flow rate. Okay. So finally, we see some results. So the major findings are, first, the gas tangential flows in membrane's helical-coil heat exchangers is significant to heat transfer enhancement. That's the average heat transfer coefficient of the membrane helical-coil heat exchangers is higher than that of the membrane's serpentine-tube heat exchangers under the same conditions. And secondly, we know that operation pressure do not have any influence on the velocity field in heat exchangers. However, high pressures can improve heat exchangers through the increase of the sinus mass flow rate. Okay, thank you.